Welcome back to part 2 of climate change. Yes, this is the last lecture of the semester. Woohoo! Yay! So let's get to business because this is the finale of the course in terms of understanding and linking together the pieces of stuff that we've learned about all semester. At the end, I'll kind of regroup and link some of the topics we've talked about throughout the semester to this particular issue of climate change. So let's get started. Your learning objectives today are as follows. We're going to compare and contrast anthropogenic, a very important term by the way, and cosmic impacts of climate change. Does that sound familiar to what we learned about last time? As a matter of fact, every single one of these is our learning objectives from our prior lecture. Today, we'll look at the scientific evidence that supports climate change so you can make your own determination. Is it real? Is it not? And last but not least, we'll look at a case study of the previous geologic climate change story, and then we'll look at some modern issues that kind of give us some perspective on climate change. Let's get busy. Let's have a quick review on radiative forcing and greenhouse gases. Which of these forcings would cause a positive forcing? Which would cause a negative? So let's start with the negative. We got to review the terms. Negative's going to be less kilowatts per squared meter. So you're going to have blue bars. And so on here, those would be the ones that have a negative number at the axis. So if you have a positive forcing, it means you're having a warming and you're having an increase in the watts per squared meter. Why is that watts per squared meter such a big deal? Because it's the actual magic thing that dictates what is going to happen data-wise with the energy budget that we learned about last time. So we're going to look at an ancient case of climate change, and this deals with a place in geologic history known as the Paleocene-Eocene thermal maximum, otherwise known as the PETM. I show this in my geology classes as well because I think it's a great story of us having a reference point before humans where climate change became a reality.
We are in the southern Bighorn Basin, and we're doing paleontology and geochemical fieldwork to learn something about the PETM, or the Paleocene-Eocene thermal maximum. And we're interested in studying the geologic as well as the biotic response to that global warming event.
The PETM stands for Paleocene-Eocene thermal maximum.
It starts at about 55.8 million years ago.
It's a period of rapid climate change and extreme change in ecosystems, in geochemical cycles.
It's a much more dramatic temperature rise than other episodes of global warming in the past.
We've got a release of carbon and a change in climate, and a lot of people are interested in it. A lot of scientists are interested in it because it's the best geological analog we have to present-day global warming.
One of the reasons the PETM is being studied in the western United States is that the western United States during Paleocene and Eocene time had a large number of deposits, sedimentary deposits that were created by rivers. And then the other part of it, of course, is that the western United States is relatively dry, and so not only are the rocks there, but the rocks are relatively well exposed, and so you can actually go and study them. So girls, let's get our backpacks on. Let's get all the tools that we're going to need for the day. Make sure we've got those picks, the shovels. What I'm hoping to see is I'm going to be looking at soil morphologic features, actual attributes of the fossil soils. And I'm hoping then to be able to say something about precipitation back 55 million years ago. One of the things that I'm interested in is soil color. You can see that some of the rocks are purple here, at least in this trench, and some of them are red. And that actually says something about soil hydrology. The red is a little bit better drained soil. This is a little bit more poorly drained. You can also see some gray models. These actually represent fossil root traces that required water to be moving through the soil and actually depleting it of iron. And some of that iron accumulated then as these iron nodules. So in fact, here are some of them. I got little iron nodules sitting on my hand. We're collecting those so that I can geochemically analyze those in the laboratory, because the amount of iron that's found in them actually correlates to precipitation at the time the soil formed. So when I look at the rocks that lie below the rocks that I'm studying, they indicate pretty waterlogged conditions. But if you get into then the overlying rocks, the beginning of the PETM, we see certain changes just in the rock types to indicate that conditions might have gotten drier. So my hypothesis at this point is that with the beginning of temperature increases, you actually get an increase in drying. You get aridity starting at that point.
We're going back to the area that's where Sarah found those leaves the other day. I want to do more prospecting around there. To find an average fossil locality is often several days of work. The first really good plant fossil locality in the PETM took me 10 years to find. It's a very rare thing, but once you find one, you can really work there for several weeks or even longer, collecting with a lot of people and find thousands and thousands of fossils. This is 0805.
Is that a legume pod?
It sure is. So it's the fruit of a legume. That's something in the bean family. And this is the end that would have been attached to the plant down here. And you can see sort of this is the shape of the pod like this. And then there would have been a seed here and a seed back in here. One of the characteristic things about the really good PETM floras that we have is that they have a very high diversity and abundance of legumes. And we don't really know exactly why that is yet, but we have two ideas. One of them is that it tends to be a family that has pretty good representation in areas where the climate is seasonally dry. The other hypothesis is that the legumes did very well during the Paleocene-Eocene thermal maximum because there was a high level of CO2 in the atmosphere, and CO2 goes up in the atmosphere, legumes become more successful, and that's been shown to some degree in greenhouse experiments today. Doug, that's that red bed that I was collecting down the ways that had the nice jaws, right? We are interested in the PETM specifically as vertebrate paleontologists for a number of different reasons, but maybe the most significant reason is because at 55.8 million years ago, corresponding to this global warming event, we see a very dramatic change in the mammalian faunas. This is a time when we see the origin of modern orders of mammals. So it's a really important time for mammalian evolution.
It looks a little bit like Frank's locality where we got the hundreds of horse teeth.
Really?
Yeah, and maybe there's a skull there too.
So we're still finding bone here on the surface, and what we've got is a skeleton of a mammal 55.8 million years old that lived during the PETM. So here's a right and left jaw of an animal called Ictosian, which is a hoofed animal that's extinct now, but back then it was a very common animal. And what's really interesting about this Ictosian is that it's very small. That's something that you see with the mammals during the PETM, is that they tend to be very small. Not exactly sure why animals are going to be getting smaller in response to a warming event. It's the right upper tree of Ictosian parts. An explanation that's been put out there is that potentially different concentrations of CO2 in the atmosphere might be causing some of these shifts in body size, and that has to do with the nutritional level of the plants that the animals are eating. It's absolutely clear that there are chemical physical and biological after effects of the warming that play out for hundreds of thousands of years. It's kind of sobering to think about that the things that we're doing right now are not going to just go away if we stop doing them.
Humans were not around when the PETM occurred, so we know that it has some other natural cause. But despite having a natural cause, not a human cause, such as global warming today might have, there is much information to be gained about modern global warming by looking at it in the ancient record.
What a great overview of looking at a historically important geologic event that represents one of the most significant climate warmings in our history. So let's take a deeper look into the PETM, talk about how it relates to us as humans today and what that might mean for our climate if we were to approach similar conditions of carbon in the atmosphere that existed back in the PETM. So, now that you know about this event, it's one of the most extreme global warming events recorded in the Earth's history. Test question is started somewhere right around 55.8 million years ago. Why is that significant? Well, let's look at this chart over here. By the way, these are microscopic organisms known as foraminifera, and foraminifera are super important for kind of gauging climate change because they're kind of picky. There are various different types that like cold weather. There's mostly warm weather type of animals. So if there's a major climate shift, we can look at the microscopic fossil record and determine die-offs or extinctions of these animals and gauge what happened because they're super sensitive to climate change. So here we are right around the beginning of the Paleocene, which is right after the dinosaur, or should I say non-avian dinosaur mass extinction event at the end of the Cretaceous. And then we come in and we're at the spike right about here, which is where we're going to see this thermal maximum. And I want you to see it starts rising right in here. What in the world could cause something like that? So understand that the beginning of the Eocene marks one of the worst events in history of warming. So we'll talk about some of the hypotheses about what this could be caused by, but the main lesson here is what could happen if we end up in the same situation with the similar carbon concentrations as they did back in the PETM. So you have to think that temperatures increased by 5 degrees Celsius average mean global temperature in less than just 10,000 years. If that doesn't sound fast in geologic reference, that's a blink of an eye. This caused a large decline of carbon isotope ratios in the ocean and land sediments, which means there was a dramatic shift in the carbon cycle. To be exact, too much carbon. So a global warming or climate change occurred. So when you're looking at this picture right here, we're looking at just about 150,000 years of deposition of sediments that represents this crazy global warming event. So scientists who studied marine sediment cores discovered that it took about 100,000 years for the Earth to get back into shape. In other words, to snap back into fitness, to get back into budget after this severe climate warming event. So that meant that all that excess carbon from this global warming event that had been sequestered in deep ocean sediments, remember limestone specifically, all of that got done before the climate started to stabilize again, it took that long to take care of business. 100,000 years. If you think about that goes back to last lecture that we talked about where the ocean has this high, huge heat capacity, and it takes a lot longer to show evidence of climate shifts, whether it's cooling or warmings. So the guy in the video said it's a little bit sobering to think about what we're doing now, even if we try to fix it, really isn't going to impact us and generations to come. It's going to be long term. He's spot on about that. So ice core data strongly indicates that natural carbon cycles are amplified as climate change shifts more than any other factor. Well, obviously we don't have an ice core available for the PETM. We had a Earth-wide climate global warming. So we do have it though. The best ice record in the world is actually found in Greenland. And it's because you can go down to bedrock with very minimal disruptions in climate shifts. So we have a nice complete ice record that captured every air molecule, every particulate matter, fossils, and so forth. So it gives us really accurate pictures as to what's been going on over the last 100,000 or so years. When we think about the Paleocene-Eocene thermal maximum, known as the PETM, the most accepted hypothesis is that these things right here, which are called methane clathrates, these are pockets of excess methane that come from ocean rock. And so they're usually at the bottom of the ocean, and if it warms too much or the acidity changes, these things start to melt. Well, the carbon's going to get released and the ocean will try to absorb it, but it can only do it so fast. So it goes back to my pumpkin pie example. It's like having that whole pumpkin pie on Thanksgiving Day, just too much of it. Your body can't handle it, so it's going to store some of those calories. Well, the Earth and the Earth's ocean can't handle it, so it stores it up in the atmosphere. And that leads us to more greenhouse gases. More greenhouse gases leads to positive radiative forcings, positive feedbacks. So you're beginning to see how the pieces link together. When you look at mammalian fauna from the PETM and you compare a modern horse to a similar counterpart from its time, wow, look at the difference. Tiny little guys, aren't they? These would be the little jawbones that they had, little bitty, put it in reference to the size of the fingers. So how can this be if we had humongo plants and little bitty mammalian fauna? Was it that we had little millions of these guys running around, or was there something else going on? The American Museum of Natural History attempted to answer that in the video you just watched. Essentially, we hypothesized that the nutrient value of the plants that they had were not that great. Seriously, I can't blame them. I am not a bean lover by any means, but most of the plants, legumes or legumes, depending on who you talk to for pronunciation, these were the main plants and food resources. How would you like to be living on beans? So these guys just didn't have a lot of weight gain, and challenged on top of that for ample water resources, food resources. So adaptation occurred, and this is where looking at the evolution and the adaptation that we talked about earlier in the semester matters. This is one of those places that shows up as a result of climate change. So let's determine historical climate change and apply that to modern history. So paleoclimatology is the study of reconstructing ancient climates and determining how and why climates of ancient times did shift. What caused them to change over time? There's a number of ways we can do this. So these are scientists that are paleoclimatologists. Paleo simply means ancient, and obviously climatology refers to the study of climate. We'll be looking at several different ways that historical climate change can be determined. So paleoclimatologists are looking at multiple factors to try to put a story together. Honestly, if they only take one of these, you're looking out of context, unless there's only one of these options available, right? So we try to do a holistic approach in science where you look at as much data as possible to try to paint a story to where you can understand and let the data drive you to a hypothesis or to proving a hypothesis. We'll be looking at ice core data, which is by far the most impressive and the most reliable. We'll look at coral banding. Looks much like some of the problems that you'll see in the Caribbean if you go diving or snorkeling. We'll be looking at tree rings and fossilized pollen, and then we'll look at the geologic rock record, specifically layers and fossils that matter. So here's some fossilized pollen on the right, and you're like, really? There's pollen that's fossilized? Well, yes. And so we can kind of determine ancient conditions by using fossil record and rock record. It's an amazing field, and I highly encourage you to learn more about it. Let's start with ice cores. As I mentioned earlier, Greenland has the best ice core record, better than Antarctica. That may be surprising. But climate scientists can document changes in the literally variations, volumes, concentrations of greenhouse gases for the past 100,000 years. You're thinking, why isn't it a million years? Because we've not had ice that long in the northern hemisphere and the northern pole. So they'll examine ice cores from Greenland. And remember I said that most of the time they can go down to bedrock, from the surface of ice down to the bedrock. These are very accurate of estimating paleoclimatology because they provide data of both what was going on in water and on land and even the air. So you're looking at air chemistry. If a volcano erupted, it's going to have some of that ash in there. If we had industry releasing large amounts of carbon dioxide or sulfur dioxide or methane gas or volatile organic compounds, those are actually captured as molecules, air bubbles in these things. If you had ancient fossils that could get in these ice cores captured in them, they're there permanently. So this is like an awesome record. It's like what every crime scene scientist wants to find at a crime scene. They want to find the ice core magic. Of course, you're not going to find an ice core probably, but the point is that it captures the data. There's no ands if buts about it. So it's important. Coral reefs develop annual growth rings, much like a tree does. So these growth bands actually get bigger when you have better living conditions. So in tropical oceans, corals produce an annual hard calcium carbonate layer, aka calcite, which is limestone, and they grow at different levels based on temperature conditions. Large corals can grow for centuries and provide very detailed climate records based on the coral's annual growth bands. One challenge that we're going to have with corals is they naturally get destroyed by nature, specifically in things like hurricanes or tsunamis. Sometimes they're also destroyed by humans, anthropogenic sources that could be for pharmaceutical purposes, medicine purposes. It could be for tourism, poor diving habits, cruise ships, a number of other there's a long list of things that can cause coral reef problems. My point is that if you find old corals and you can get the banding from it, that tells you some really quality information about the history of that area. Tree rings, the third item on the historical climate information. Like corals, trees experience annual banding. As they grow and you have good growth spurts, the band should be wider. If it's not so good, it's going to be more narrow. I might also just throw out a hint here. It's kind of like mammoth tusk. They do the same thing. So the bigger the mammoth tusk ring, the more food the animal had to eat. So the smaller the ring, the more they were starving. So it's kind of like how tree rings work. Some trees live for hundreds of years, and it's possible to bore a cylinder out of an old tree and study its rings for indication as its area's historical climate. So some of our oldest trees around the globe, when you look at the sequoias and you're looking at, for example, the Redwood National Forest in Northern California, you go to New Zealand and you look at the special trees there that are so old. This can give us a glimpse at how conditions might have changed for the climate. The geologic rock and fossil record, great stuff, but keep in mind it's not as accurate in terms of capturing all that really good concentrations of stuff that's in the air and in the water that we've done in modern time, because rock layers aren't made that fast, especially mud at the bottom of the ocean. It takes about 1,000 years just to get about a third of an inch of deposition at the bottom of the ocean on normal circumstances. So the geologic rock layers and fossils also demonstrate historic climate of an area. Rock cores are examined by scientists to identify past environments, because in these cores, you'll take a core boring with a hollow auger stem drill, and then you'll slice it in half, and you'll actually look for changes in the type of deposition. You'll look and see if there's coal bed layers, if there's something that changes the color, fossil concentrations, and we even look at the microfossils like foraminifera. So petrified wood would indicate that the area was once a forest, or fossilized reptile bones, if you found them in a core sample, could indicate a possible present-day tundra. So if you're looking at these, you can start to determine if an area is once considerably warmer, cooler, simply by looking at the sediments. So let's talk about anthropogenic climate change. Anthropogenic climate change is human-based climate change. So let's look at the term anthropogenic. Anthro referring to human, pogenic referring to source of change. So climate change caused by human, including but not limited to greenhouse gas emissions, dark aerosols, CFCs, which are the stuff that make your chlorofluorocarbons, things like your refrigerators and freezers cold, and your air conditioning units cold, and deforestation. So all of these factors change the budget that we learned about in the first lecture, and if we have too much of a good thing like greenhouse gases, this can change the chemistry of our atmosphere. So let's say we have too much greenhouse emissions, that's going to trap more heat there. Let's say we have dark aerosols, those are going to absorb heat, the same thing's going to happen. So deforestation is going to cause less heat to be absorbed at the surface, because remember, more forest, darker surfaces, darker albedo absorbs energy. So you might have more reflected back to space, so that could cause a cooling. So not all anthropogenic things are leading to global warming, and you hear that. So I wanted you to kind of take that similar look. As we watch this next video, I want you to take to heart kind of what you're seeing and understand the importance and relevance, and then I'll revisit what this all links to in our study.
On Earth, we have a lot of water locked up as ice, particularly the poles. You get really big piles of ice, and we call those ice sheets. These ice sheets are great indicators of what's going on in our climate. So there's a lot of investigation. Are they melting? Are they not melting? Because if they do melt, they raise sea level. That affects everybody in big ways.
It's the edge of the glacier right here. Go? Yeah. Go straight over the glacier right here.
We're at the Russell Glacier, which is a small outlet glacier on the edge of the Greenland ice sheet. A glacier is ice in motion. It's flowing under its own weight. If you were to stand here with a camera day after day, what you would see is the ice marching towards us and falling off and falling off. We say the Greenland ice sheet is melting. The way that happens is the outlet glaciers speed up. When the outlet glaciers speed up, more ice breaks off in the fjords. It's not as if the entire surface of the Greenland ice sheet is melting. The actual melting of the ice, most of that takes place at the coast.
Yeah, for Greenland, what we're seeing is quite a bit of change, and I think a lot of the change is surprising a great number of scientists. You know, glaciers around the world are melting, but they don't hold all that much water. Greenland has about 7 meters of sea level equivalent, so if that ice sheet melts, all of it, we'll get 7 meters of sea level rise. That's over 20 feet. If the West Arctic ice sheet, the one down in the southern hemisphere that we're worried about, melts, that could give us 5 meters of sea level. So up to about 40 feet of sea level could result if we melt both of these ice sheets. It's pretty important to look back at the last time sea level was higher than present day, because you want to figure out, could we in the future go across that threshold?
We're standing here in one of my favorite places in the world, which is Windley Key Quarry, Florida, in the Florida Keys. And if we had been here 125,000 years or so ago, we'd be underwater by several meters. What you see here in the quarry walls on either side of us here is a rock called the Key Largo Formation. It's a limestone, and about 30% of it is composed of corals that were once part of a living coral reef that formed about 125,000 years or so ago during a period we call the last interglacial. This is a remarkable example of a brain coral in its original growth position. Diploria, or brain corals, are one of the most common constituents in the modern reef off Florida today, and here in the Key Largo limestone. The top of the coral head is here, and you can trace this along the sides, down here to the base of the coral. The top of the quarry here, and very close to the top of this brain coral, are about 5 meters above sea level. And brain corals need to grow in water at least 3 meters deep or so. So that means that sea level has to have been probably anywhere from 6 to 8 meters higher than present during the last interglacial period. One of the most powerful things about the geologic record of sea level change is it does answer the question, is such a thing possible? We know it's possible because it's happened in the past.
Well, it's not hard to take what we know about the height of coastlines to get maps showing as sea level rises which areas will get flooded where. Here's a visualization showing the Earth and the areas in red that would be submerged with 6 meters of sea level rise. So 6 meters of sea level doesn't sound like very much, but it'll affect a very large part of the world's population and landmass. When we zoom in to finer spatial scales, it allows us to put a more human face on the sea level rise that could occur in the future. We can actually see individual communities that will be submerged by sea level rise. Science is never certain. What science is all about is trying to figure out what's probable, what's not probable, and to be really open with what the uncertainties are. In this case, we know the sea level was higher in the past. And we know that was because the Earth was warmer, particularly in the northern hemisphere, over the Greenland ice sheet. The big question is, how much warmer was it? And both our climate modeling and our paleoclimatic reconstructions suggest that somewhere between 3 and 5 degrees C is the temperature by which a lot of Greenland will be melting fast. But to put it in a little perspective, 3 to 5 degrees, how long will it take us to get there? Just in the last 50 years, we've warmed up the Arctic by over 2 degrees. So we're more than halfway to 3 to 5 degrees. And sometime later in the century, we'll cross that mark. In our work, we don't know for sure where the threshold is beyond which the ice melting is inevitable. But we know it's coming, and if we don't do something about greenhouse gas emissions soon, we're going to cross that threshold, and future generations are going to have to deal with that big sea level rise.
Sobering moment, isn't it? to listen to what he had to say, that we're more than halfway there in terms of temperature to start melting the Arctic, much like we did in geologic past. So they showed you brain corals in that video, an example of how we can look back and trace the past and interpret paleoclimatology. This is not some make-believe story. This is documented with scientific data. There are rocks, there's fossils, there's tree rings, there's coral rings, there's ice cores that all support that we're having a shift in our climate. Understand that shifting in climate can work both ways. It can be a global cooling, it can be a global warming. You don't hear about the coolings as often. But shortly after we get into a global warming, the Earth will probably snap itself back in to shape by adjusting the temperature of the ocean currents to try to sequester that carbon and get back into shape again, so it can lose a little bit of that excess carbon and other greenhouse gases. That'll snap us back into a global cooling. So there's so much to the story that is complicated and intriguing at the same time. So let's talk about anthropogenic climate change and kind of put the story together for you. Geologic sediment and ice core data indicate that carbon dioxide levels, CO2 levels, must double the pre-industrial revolution levels of carbon. That's 280 parts per million by volume. Let me say that number again. Pre-industrial revolution levels of carbon were 280 parts per million by volume. So what does that look like in time frame? Somewhere in the 1700s, like 1750-ish, when we started using coal as a main source of heating. If we have a doubling of pre-industrial carbon concentrations of 280 parts per million, and you double that number, you'll achieve a 1 degree Celsius increase in global mean temperature. So if global mean temperature increases or has increased between 3 degrees to 5 degrees Celsius, the carbon level would exceed the Paleocene-Eocene thermal maximum's carbon level of 1,000 parts per million by volume. I just need you to get a calculator out for a minute, or get your phones out and get the calculator function on, and let's look at this. Do 280 times 2, then add it again, then add it again, and add it again, and see if we're not at a worse place than we would be at PETM values. Your number should be shocking. And if it isn't, do your math again. And then I want you to think back to the small little mammalian fauna that we looked at. Is that our fate? That's one of the questions I have for you. So if we reach this 1,000 parts per million by volume, by the way, that's a test question, that 1,000 marker is kind of like a big number that you need to know. What would this do to the polar ice caps like Greenland? You heard the scientist in the American Museum of Natural History in both videos you've seen this morning or today. You've seen them describe that would cause it to melt quickly. So recent climate change studies have supported this documentation. The United Nations World Meteorological Organization, known as the WMO, released its report in 2011. It has determined that carbon dioxide, methane, nitrous oxide, known as NOx, levels are at the highest that they have been in several million years. Because remember, we also have that ice pack down in Antarctica that gives us a couple of million years of data. It's just not continual data. This report also stated that when compared to air quality samples taken from ice cores, the average global carbon dioxide was the highest ever recorded, currently resting at 390 parts per million by volume, which is a 2 ppm rise since 2010. So I want you to understand, we have been rising substantially. You're like, okay, Let's go back and look at that number. 280 parts per million for pre-industrial revolution. Here we are at 390. You're like, well, that only took us like, 300 less years to do. Most of that has occurred in the last 50 years. So we're growing and increasing our greenhouse gas emissions, and we're stuffing pumpkin pie on a regular Thanksgiving day, almost every day, more than the atmosphere can handle. So the ocean can only do so much limestone cranking out to try to compensate for it, just kind of like your metabolism, and we're ending up with a problem we can't solve. So let's look at our science servings, and we'll have a few more things to say about this, then I'm going to talk about how it all links together. Another side effect of increasing global temperature involves permafrost melting, and that creates a drunken tree effect where they tilt over and they kind of stumble over. As this occurs, here's why. Once melted, the permafrost emerges and the soil becomes very loose and swampy, so the trees don't have a foundation to sit on. So as permafrost emerges into a type of massive mud pit, resulting in ground failure and mass wasting, unfortunately, not just for the trees, for our climate, methane emissions are released to the atmosphere. Going back to the PETM, the methane clathrates, are you seeing a pattern here? Permafrost is in the Arctic, so anywhere that you're going to have these conditions, and actually it's all this, you can find permafrost anywhere in the world that has the right conditions for it, southern and northern hemisphere. But in the Arctic Circle, this is a problem because we got so much permafrost that's caught up there. The Intergovernmental Panel on Climate Change, known as the IPCC, you should know what that is. The IPCC assesses the scientific and technical and socio-economic information relevant for understanding the risk of human-induced climate change. Remember the term for human-induced? Anthropogenic. In 2016, the 43rd session of the IPCC decided to prepare a special report, like one of those important take notice reports on climate change, the oceans, and the cryosphere. Cryosphere refers to all the ice on Earth, which requires several years to compile. So the information still in the works of being made. Have you decided that climate change is a myth or a reality based on what you've heard thus far? Is there any truth to it on one side of the pendulum for climate cooling, climate warming, or is it just a big hoax? That was the purpose of this lecture. So now that you've kind of heard all the news, and you know that every time we double pre-industrial revolution carbon concentrations, we raise our global mean temperature by 1 degree. You know what's happened in the PETM and to the mammalian fauna as a consequence of the climate warming. And you know that our population is growing exponentially. Our resources are diminishing, which affects our biomes as the temperature changes, climate shift, latitude's going to change where certain biomes can exist. We're going to see potential extinctions. We're going to see invasive species that can thrive in areas where they didn't used to. Let me link all of this to kind of our test 2 unit. Let me link this to kind of the second group of major videos and lectures you saw for this semester with regulations. Environmental regulations are passed in order to try to help control this problem. So when I worked for the Texas Commission on Environmental Quality, one of the important elements of rulemaking was that humans that were interested parties, such as small businesses, industry leaders, local government leaders like city officials, they were involved in the rulemaking process, so it makes sense. Because the environment is where we all live. So it's not just about clean ground, clean air, clean water. All of this fits together. It's a holistic, cumulative thing that plays a role in human health and the environment, and especially the biggest picture, which is climate. Having a stable climate is not going to happen. Geologic past has shown us time and again that climate has a pendulum shift. The question is, in human existence time frame, in your lifetime, your children's lifetimes, your grandchildren's lifetime, are we going to have a pendulum swing? And if so, what does that look like? How do we survive that? How is a population over 7 billion reaching 8 billion able to support such a thing? You begin to think about this, and you begin to think about all the things you've learned this semester, and you realize they're all connected. So I'm hoping that as you've left this semester, that you are more in tune, more data-driven about what's out there and how the pieces of environmental science fit together. So I want to take a moment to ask you the same question. Have you decided if climate change is a myth or if it's a reality? That's a decision only you can make, but hopefully I've helped you at least get the science side of the view and maybe some of these socioeconomic aspects as well as we've made this journey together through this semester. So I want to thank you for taking environmental science, and now that you have all this foresight about what could happen, what do you want to do about it? What are you going to do about it? And who are you going to let know that these things are out there? Hopefully you consider taking Environmental Science 1302. It's the second part of this course. If not, I'm so glad you decided to take Environmental Science 1301 with me and enjoyed having you as a student. It's always incredible to share our world's environmental issues with students. It's an honor and a privilege because as someone who's been trained in this field, I feel responsible for giving that information back to you. Great semester, folks, and this is the last video of the semester. Bye.